Good afternoon, everyone. I'm Jeremy Picot-Clemente, Photonics Technology Manager at EPIC, and I'm really pleased to welcome you for this online meeting on micro LED for automotive application. So as the automotive industry continues to evolve at a rapid pace, it's important to stay up to date on emerging technologies that have the potential to transform the driving experience. So today we will be focusing on one such technology, micro LED. So thank you for joining us for this discussion on micro LED for automotive application. So our goal today is to share insights, spark ideas, and inspire collaboration among those who are driving the future of mobility. So before this, few words about EPIC. EPIC is the largest industrial consortium in photonics, acting as a catalyst of the European ecosystem at a global scale. EPIC will celebrate this year its 20th anniversary and has over 800 members, including companies, research organization, and other stakeholders in the photonics industry. And its members covers a wide range of photonics applications, including healthcare, telecommunication, manufacturing, space, PICs, quantum, among others. EPIC provides various services such as market intelligence, technology foresight, and networking opportunities. EPIC is actually dedicated to support the growth of and competitiveness of the photonics industry. Here is the EPIC team made on 11 people, all passionate by photonics. So this team is dedicated to support members from the marketing to the technical sides. You can find here next in-person and online meetings we will organize in the next few months. So we'll have the AGM in Helsinki, end of March, in-person meetings covering a wide range of photonics applications. So fiber sensing at HBK in Porto, AirVR at Jabil in Jena, micro-optics, laser processing, and PICs during Laser World of Photonics in Munich, end of June. And after summer, we will have, in September, two important events on Photonics for Space in Kielce, Poland, and Photonics for Defense, sorry, in Kielce, Poland, and Photonics for Space at Excel, close to Paris in France. And about online meetings, the next OTM will be the 24th of April on Photonics for Climate Change Monitoring. And after this, we will have OTM on additive manufacturing, agriculture, micro LED for consumer electronics, which will be organized in collaboration with the International SSL Alliance, and Photonics for wearables in July, before the summer break. Here is the value chain distribution of all the companies who were registered for this today's event. And as you can see, and maybe already know, one of the strengths of EPIC is to be able to gather startups, SMEs, and big companies from the beginning of the value chain, from design photonics components to the end, with end users, system integrators, as well as services providers. And I would like, of course, to thank all our today's speakers. So Paul-Henri Matha from Volvo Cars, we will talk about micro LED for automotive lighting, stakes for car maker. Vogel from Fraunhofer FEP on heterointegration of emissive front planes onto SI-CMOS backplanes for micro displays and sensors. Jankus Meulen from Morphotonics on large area nano imprinting for automotive application. William Liu from AUO, micro LED displays are quickly becoming prevalent in super luxury and sport vehicle. Kunal Kashyap from Porotech on DPT, which means dynamic pixel tuning, the ultimate solution for micro displays. Benjamin Willeke from Forvia on exterior displays for automotive. And last but not least, Vygintas Jankus from CEA-Leti will have a talk on micro LED technology at CEA-Leti. So thanks to all the participants, the speakers, of course, for their highly relevant contribution. And we hope that you will enjoy this OTM. And last important thing, please feel free to ask questions during the Q&A session after each presentation. So now we can start with our first speakers, Paul-Henri Matha from Volvo Cars. Please, Paul-Henri, I'm stop sharing my screen and you can start your presentation.
Okay, hello everybody. So I think you see my screen. So I'm Paul-Henri Matha, I'm the technical leader for exterior lighting. So indeed, I did this presentation, I think 3 years ago in July in EPIC. It was a quite similar presentation, but then I have updated this presentation with the final status. So I just mentioned one OEM insight about micro-LED technology, because we can use micro-LED technology in a lot of usage. So it can be in lighting, so what you have on the left side, when you put light on the road to be able to see. But after you can use micro-LED technology also for signaling purpose and communication. So it is what we call signalization to be seen. But I will focus especially on lighting. Yeah. And then my focus will be also on lighting about low beam and high beam and what we call adaptive driving beam. And the idea of this technology is to put the maximum light on the road to have the best perception on the road. And then the idea is to have adaptive driving beam with partial high beam that will not glare on coming cars. So it is exactly what you see there. So you have a camera on the car. So you drive your car, you have a camera, and then you detect a car like this one, and then you will not put light on the oncoming car, so you will not glare, but you will have light on the both sides on the vehicle. And then you can go on the right picture, and if you have a low-cost system, I will say that you will have a big dark area between the car and the road, and if you have best-in-class lighting technology, so especially with HD technology, so with micro-LED technology, you will have a smaller dark area, and you can see that, for example, with this additional light you have on the side, you see the pedestrian, and then if you have a simpler concept without micro-LED technology, you will not be able to detect the pedestrian on the picture. So this is the benefit, or one of the benefits on the micro-LED technology for automotive lighting. Then what you can see also, it is some different concept we have today on the road with just I am moving something. Yes, on the road. So it is what we have here. It is 84 pixels. So it is not micro LED technology for the moment because it was 84 pixels. So 84 chip of LEDs. And then you have this sort of module, which is well done. It is what we have on Volvo XC40. It is on Polestar 2. It is on Mercedes E-Class and so on. And then you can see that this pixel, you have a lot of pixel on the road, and then you project light or no light, because you see you will not glare the pedestrian, you will not glare the oncoming driver if you decide to have light or no light. Seems that I am stuck. Okay, so what are the stakes for lighting? So the usage of micro LED technology is to do a high definition headlamp. And then what we want to have in the beam pattern is to have around 2000 lumen for the low beam on the road and 4000 lumen for the high beam plus low beam on the road. We want to have a very large field of illumination or field of view, 90 degrees. So then the driver will see the scene with light everywhere. And the vertical field of illumination should be around 20 degrees. So 15 degrees down and 5 degrees up, something like this. We have to focus on power consumption because we do not want to spend 1000 watts, for example, to be able to do that. We have to be able to have a small packaging also. And we have to have also a high definition system, so a resolution to have the maximum accuracy. And then the resolution should be around 0.1 degrees, something like this. So what we have today on the road, it is on the Mercedes S-Class first, and we have it, for example, in Volvo now on the EX90 and Polestar 3. So it is a DLP technology from Texas Instruments. So indeed, we have a big module inside the lamp. You can see the size, 150 millimeters by 150 meters by 150 meters. Very high power consumption, also 60 watts, but a reduced field of illumination. So I mentioned that we should have 90 degrees, but we have indeed plus or minus 7 degrees only. So it is very reduced field of illumination. But then we have more than 1 million pixels. And then with this sort of module, we need to have an additional module to be able to do the complete illumination. And when you see with this module, the solution we need to have something around 200 watts. So it is 4 grams CO2, and it is not so good for power consumption and also for CO2 emission. About micro-LED technology, so soft proposal was developed by Valeo. I think it is a presentation from January 2020 with 25,000 pixels. And you can see that power consumption is still quite important, 55 watts, but the packaging is reduced. So it is a smaller packaging than the previous solution. And also you can see that they've reduced the field of illumination, plus or minus 70 degrees compared to plus or minus 7 degrees, but you still need an additional module to be able to do the complete illumination. So last time, it was in July 2020, I said, what should be the target for micro-LED technology and micro-LED lighting industry? I define a size of the module, something like 80 by 80 by 100. I provide also estimated power consumption target, 30 watts, and the estimated horizontal and vertical field of illumination. And then I said that we should not have additional module to be able to do the low beam and the high beam. And then now I want to show you what is the status on 2023. So we still need to have an additional module to be able to do the low beam. But for the high beam, it is possible today to do it with a 2 HD module. And then, so we have some proposal from Lumiled, for example. So Lumiled technology, it is what they presented in DVN Paris, so in January 2023. So you see the chip they are using, and you see with the module, what is the size of the module, and you see also which field of illumination they are able to be. So you can see for the horizontal field of illumination, they do 21 and vertical 7 degrees. So it is not exactly what we would like to have, but it is a bigger field of illumination. Also, I put also another presentation from Osram, which is a competitor to Lumiled, and they said that, okay, with 2 modules, also we can do the complete field of illumination. It is what you see on the right picture. You use one to have a good resolution in the center of the road, and you use an additional one, which is a red one, to do the complete field of illumination of the high beam. And then with 2 modules, you can do the complete high beam. And then you have also a chip with 25,000 pixels. You have also some different version with less pixel, but with a different field of illumination. And then we can see that today with 2 modules, we can do the complete high beam illumination. And what we will do tomorrow? So tomorrow, the idea is to do still the complete field of illumination. So I put a roadmap also I have seen in DVN Paris in January from MIND. So the question is, how can we work together to reach this target? Thank you.
Thank you very much, Paul-Henri, for your presentation. It's really interesting to get your inputs. I mean, for this topic. So, any question for Paul-Henri? Please raise your hand through Zoom. You can find the button at the bottom of the screen. Yes, Harald, please, from SUS Micro Optics.
Yes, thank you, Paul-Henri, for the presentation. If you talk about modules, what is the interest of, or what is the remaining styling possibilities in a headlamp if you have this kind of more or less standardized module?
What I can say for the moment, we have some issues with the size of the module. Not the packaging size, but the design size, because what we have seen in the HD technology for the moment with micro-LED, we need a height of a module which is around 40 millimeters height. And a lot of design, currently, designers, they would like to have a height of 20 millimeters, 15 millimeters height. You can see that on Lucid cars, on Jaguar Land Rover, also Volvo. So Volvo solution, for example, is to develop an ultimate hammer. Perhaps you have seen it on X90. So we hide the module and we open the daytime running lamp to see the module, and then we can have a higher height for the module. But the trend is to have very thin modules, so with height below 20 millimeters. So this could be a problem because with the chip and the direct imaging lens we have from lamp supplier, we need more than 20 millimeters height today.
Thank you.
Thank you, Harald. For a question, yes, Emily Viasnov from Synopsis, please, Emily.
Yes, thank you, Paul-Henri, for your presentation. You listed many specifications that and a roadmap as well that we need to achieve to get that one ultimate module for high and low beam. I was curious about, to your perspective, what is the remaining challenges? Is it about the cost? Is it about the size of the chip? Is it about the brightness? What is the main challenge that we are still facing to get there?
The main challenge, I think, we have no LED chip first. If we want to do the complete illumination, for the moment we have not this solution. So we have maximum 20,000 chip. I think we need 100,000 chips. So we have some roadmap from LED suppliers. But then after, we will have some problems, I think, with the power consumption. Because today with the 25,000 chips, we have a power consumption about 50 watts. If you multiply it by 4 to have 100,000 chips, then you will go to 200 watts, so it will be too much. So we have to define something more efficient. And it will be the main problem. And efficiency today of the solution is not so good, because you have a lot of LEDs, a lot of lumen, but at the end, the efficiency is around 30%, something like this. So the optical system should be improved.
Emily, you want to add something?
No, thank you. Thank you very much.
Thank you, Emily, for a question. Any other question, please, for Paul-Henri? Okay, so if you want to get in touch with Paul-Henri, you can still contact me after the meeting, and I will be pleased to put you in contact with him, of course. So thank you very much, Paul-Henri, for your
thank you.
Relevant inputs. Thanks a lot.
Bye-bye.
Thank you. And okay, our next speaker is Vogel, so Director of Microdisplay and Sensor at Fraunhofer FEP, and he will have a talk on hetero-integration of emissive front planes onto SiCMOS backplanes for micro displays and sensors. So please, you can start your presentation.
Hello, everybody, and thank you for inviting me for this talk here. By the way, can you see my screen?
Yeah, it's good. Okay.
So, well, I will give a little bit an overview on hetero-integration of emissive front planes onto SI. SI stands for silicon, CMOS backplanes for micro displays. And I'm with Fraunhofer. I'm with Fraunhofer FEP. FEP stands for Fraunhofer Institute for Organic Electronics, Electron Beam and Plasma Technology. We are based in Dresden in East Germany. Well, I mean, we operate 6 different core competences at our institute, and the 3 on the bottom here. So IC design, IC stands for integrated circuitry. Then organic electronics, which is important for our OLED front planes, and also plasma-assisted large area and precision coatings. These are the core competences that go into this work on emissive front planes for micro or on emissive micro displays. So that means we are able to do the backplane IC design. So typically a micro display comprises millions of individual emissive pixels that have to become addressed and individually driven, and that is performed in the very highly integrated circuitry or backplane circuitry. And so the backplane is the underlying chip that addresses all these millions of pixels, and the actual front plane is what then provides light. In case of emissive micro displays, there is obviously an emissive front plane, and we do that in terms of OLED, so organic light emitting diodes, and therefore we perform the OLED post-processing in our own line on 200mm substrates. Whereas the silicon IC backplane substrates are performed on both 200mm as well as 300mm processes. So the OLED so far are being processed on 200mm, and with partners we also work on micro LED integration on both 200 and 300mm backplane wafers. So to give you a quick overview on micro displays in general, so these are devices that are physically very small, so typically less than 1 inch screen diagonal, but comprise very high information content. So at least TV quality. So, and that translates into more than 1000 pixel per inch. So typically we talk about dot pitches. So a dot would be a subpixel and of 2 to 5 micron, something in that range. And that again translates into up to 5000 ppi. Some also report results in 10,000 ppi or so. So, and that makes an active matrix substrate, that is the silicon CMOS backplane, necessary. And that also comes typically with low power consumption, but always the actual screen is so small that you always need an magnifying optics to perceive an enlarged image view. And this can be by a virtual projected image or by a real projected image. So, and obviously those micro displays have their place in projectors, but also in near-to-eye optics, for instance, or near-to-eye displays, like for instance those electronic viewfinders, like in this camera, but of course also in head or helmet mounted devices. So, like here, for instance, in a head-up display in a motorcycle helmet, but also in AR, VR, MR smart glasses. So this movie gives you just a little bit of an impression of those micro displays. So rather tiny devices, obviously, but they can even go up to 1-inch screen diagonal, as you see for this WUXGA resolution micro display. All the front planes that light up here are made in OLED in these examples. Okay, and since we are talking about emissive micro displays, so one of the options is obviously micro LED, and that is the major focus of today's talk, and that is related to 3.5 on silicon. And there we have some sort of hybrid heterogeneous integration approach. So that means we have multiple substrates. We have one substrate where the micro LED come from, so on 3.5. Gallium nitride, for instance, substrates, and the CMOS substrate is obviously coming from a silicon wafer. And for OLED on silicon, in contrast, it's a monolithic. So we have a sole substrate, and the OLED are being deposited on the silicon CMOS substrate. And emissive micro displays in general have a very simple advantage versus all other technologies or approaches, since for near-to-eye displays, you only need, let's say you have the emissive display, so the modulations, image modulation source and light source in a single device, and then you need just a projection lens, and that is what you can get into the eye. And all the other devices, all the other approaches need significantly more devices to make a complete system. So I don't want to go into details on AR versus VR, but for head-mounted devices, we compare fully immersive, so which is kind of those VR headsets, versus optical see-through, like the HoloLens or like this device, or also look-around devices. And look-around actually is the first the first Google Glass was also a look-around device. Although you could look through the optics, it was actually carried above the line of sight, so you were actually looking around or underneath these optics to perceive your real view, and you moved your eye up to perceive the virtual view of the virtual image. So if you compare those requirements, and also add to this comparison head-up display applications like in automotive or in avionic, then you come up that specifically for luminance. There are very high luminance requirements, mainly for optical see-through smart glasses, so more than 5,000 nits, as well for head-up displays. So typically they specify 10,000 nits up to even 1 million nits. And on the other end, we have also very strong requirements with respect to power consumption. For instance, such a look-around device, or like this one, these are truly wearable devices. So with very low battery capacity. So that also means that the power consumption of those devices has to be very small, so less than 10 milliwatts. And to give you an idea, a regular micro display on the market, either OLED or micro LED, at let's say 90 Hz frame rate and a certain resolution, then typically the power consumption starts at about 100 milliwatt and goes up to 1 watt depending on frame rate and resolution and so on, and luminance of course. But in variable applications, battery life is very important, and then you really need ultra low power consumption. Okay, and now micro LED obviously comes with a promise to achieve a very high luminance output, and for the applications that I showed before, that is something that is definitely required. So then a little bit to compare on the driving side, OLED versus micro LED. So for a single unit OLED, so for instance a white one, you typically need a forward voltage, threshold voltage of 2.5 up to 7 volts, and if you have multi units which are used to achieve higher brightness, so more than 10,000 nits for instance, you definitely will have more than 5 volts. But the thing is that the efficiency maximum, so the current and power efficiency maximum of OLED is in the range of 1 to 100 milliamps per square centimeter, and that's a little bit in contrast to micro LED. The driving voltage might be a bit lower, but the efficiency maximum is significantly higher. So they reach the efficiency maximum at about 1 to 10 amp per square centimeter. And that definitely also has an impact on the driving concept with respect to the pixel cell principles. So if we all sum up, then definitely micro LED have some expectations with respect to higher luminance, higher than OLED in that case. So both are emissive, micro LED as well as larger ambient and operating temperature ranges. So OLED specifically at very high current densities or power densities gets rather warm, and on the other hand, the OLED materials themselves have an issue, at least if they are very highly efficient. They also have an issue with temperature stability. So micro LED, also one of the expectations is to actually achieve temperature stability at very low, or at temperatures significantly higher than 85 degrees Celsius, which is important in automotive. Then also micro LED expect to become or let's say can be switched much faster than OLED. But I mean, on the other hand, what means much faster? So for OLED, we at phosphorescent OLED, we can switch in the lower microsecond range, and for fluorescent OLED, we can already switch OLED in the upper nanosecond range, and which is already quite fast. But micro LED could still a little bit faster. And on the other hand, what I would expect from micro LED is a narrower bandwidth than OLED, which would yield a higher spectral purity. And also short coherence could be an issue. But all the other items that I marked here in yellow, for instance, current power efficiency, longer lifetime, and reliability, and also, let's say, wider wavelength ranges or tightened emissions angles or higher pixel density, I think there's not really so far decided if micro LED can provide advantages there. And last but not least, on the cost side, at least to what I have seen and heard today, OLED on silicon is much more mature. Of course, I mean, it's existing for some years already, and at least for the next few years, I really foresee that micro LED and micro displays will still be on the high-end cost side. But on the other hand, micro LED on silicon can really provide, let's say, also let's say EU value chain. So that means most of the processes, most of the technologies that are needed for micro LED micro displays are really available in Europe. And well, I mean, that is probably something that EPIC could also promote to set up such European value chain. So this gives you some idea of maximum current densities or also individual currents per pixel that we can drive from various backplane devices that we have available, so up to about 4 amps per square centimeter, and starting from about 1 to about 4. So that means these are platforms that can be used for both OLED as well as micro LED backplanes. And since I mentioned the ultra low power requirements specifically for wearable applications, that is a backplane where really that is a very specific backplane architecture, and that provides the opportunity to make a display really in the 1 milliwatt range, either for OLED or micro LED. So to conclude a little bit, high brightness will definitely be let's say a requirement for those embedded projection applications that I mentioned, but also for some other applications like optogenetics. High pixel density are definitely important, for instance, also for light field and holographic displays. I will skip that. Then extended spectral emission and detection ranges. So that's why we are talking about micro LED. And of course, we also talk about new form factors, for instance, transparent microelectronics. So the backplanes that we are currently making on silicon CMOS are typically intransparent in the visible spectral range, but we are already working on an approach, and we already can show first samples that will make such silicon backplane transparent as well, and that provides new approaches for optics. Okay, and maybe already an outlook for SID Display Week in LA in May this year. We will show a 2.5 micron dot pitch OLED micro display on a 28 nanometer backplane on 300 millimeter wafers. So that is also something into the direction of very high resolution. Okay, thank you for paying attention to my presentation. And here are some, let's say, some hints where we are also seeking collaboration, for instance, also with customer and application specific components and devices. And so also we ask our customers and partners for application specification, and also we work with customers for manufacturing technology and pilot fabrication. Thank you very much.
Thank you very much, Uwe, for your presentation. Really interesting overview of what you can provide to the market for this kind of application. So do we have any question for Uwe? Yes, please. I don't get your... Yeah, Alexander, please, from Allo Semiconductor.
Yes, hello. Thank you, Dr. Vogel. Hello. Question, I'm curious about the automotive applications. Could you also build such an array for automotive application with micro LEDs?
Yeah, I mean, let's say the processes that we are using for the CMOS backplane are automotive qualified. So they are qualified up to 125 degrees Celsius. And in general, so let's say also the processes we are for the backplanes, let's say we are really accessing from foundries. So as you can imagine, you need an let's say rather specific, as we call it, top metal interface in between the CMOS backplane and the whatever emissive front plane it is, either OLED or micro LED. So therefore, you need to really adapt the CMOS backend. But since we do that in, let's say, fully qualified foundries, mostly in Europe, which are in their base processes are also qualified for automotive. So the answer is yes.
Okay, thanks a lot. I also support your request for EPIC to continue build the value chain on micro LED.
Thank you, Alexander. Feedback and question. Yes, Kunal, please, from Porotech.
Hi, Uwe. Can
Hello.
you hear?
Yeah,
Hi.
I can.
Yeah, my question is more related to the automotive application. It's very clear that CMOS is very powerful for the near-eye applications like AR, VR and all. But in HUD type, where automotives are looking for more than 3-inch and 7.3 to 7.5-inch, 8-inch, that range of the size, how you see that CMOS is going to be compatible in terms of the performance and the cost, where we are talking about say TFT backplanes.
Yeah, so the only approach I see is to have a kind of a distributed approach. So you don't have a, let's say, single die, but you have multiple dies that are distributed on a larger substrate. And specifically with micro LED, where you can have a rather, let's say, or significantly higher luminance than for OLED, then let's say a kind of a rather low fill factor does not matter too much, at least let's say in terms of head-up projection, also head-up display projection. I mean, for the applications that we have seen before from Volvo, there it might be different. But if you think about automotive head-up displays, then I think this could be really a solution, let's say, to have a 3-inch whatever substrate, glass or PCB or whatever, and let's say then to have let's say clusters of let's say tinier micro displays spread across a larger substrate, and but of course, let's say those tiny clusters would have to be individual micro LED micro displays. Okay. And of course, they have to connect to each other and so on. But I mean, and optically combined. But in general, I think that's the approach to be cost competitive.
Okay, so in terms of like tiling type of things,
putting
micro display tiles.
Yeah. Mm-hmm.
And in terms of the cost, because CMOS is a very expensive, if you are using 12-inch, 28 nanometer node, then
again, tiling, maybe tiling is not the right term. Let's say, if you think of tiling, then you think of devices that let's say, that touch each other. So, but here we would really have, let's say, tiles that are spread from each other. So there you have a rather low fill factor across the rather large substrate. So you know what I mean? Okay. And so therefore the effective silicon die area and therefore cost should hopefully be manageable.
Okay, thank you. Thank you,
Kunal, for a question. Yes, Jan, please, from Morphotonics.
Yeah, thank you for the nice talk. You look for ways to enhance the output and also the direction of the light. Would it be feasible to add optical layers, micro lenses on the micro LEDs, or OLEDs? Is this a route forward? Possibly by imprinting?
Definitely. I mean, we have thought about this for OLED for years already. And let's say specifically also for OLED to be able to, let's say, to narrow the emission cone. Since specifically in near-to-eye applications, you always have an optics with a limited numerical aperture in front. So that means those light that is being emitted outside this NA of the first optical element is actually skipped or does not contribute to the virtual image luminance. And therefore, we have thought about integrating microlenses on top of our OLED for years already. But how to say is this? Well, I mean, you have to consider, or you have to take into account that the individual pixels that we are talking about, either for micro LED or for micro OLED on silicon, are in the range of 2 to 5 micron individual dots. So in that range, I mean, there are also larger ones, but I mean, let's say if you would like to have a rather small and cost-effective chip, then and you want to have a certain resolution, high definition, whatever that means, but then you need to come up with pixel sizes or dot sizes at 2 to 0.5 micron. And then you need that kind of, let's say, optics, micro optics, that, how to say, that are able to collect most of the light from your either OLED or micro LED dot area. So, but typically to achieve that, the micro lens has to be larger than the actual, let's say, emissive dot, and by that you again lose space. So that's kind of a trade-off. But in general, let's say, to enhance the light outcoupling, or to maybe even have, let's say, the optical elements directly on top of the emissive pixels, that would definitely help. But also, let's say, their collaboration is required and requested by us.
Yeah. Okay, thanks.
Thank you, Jan, for your question. And the last question, please, short question, short answer from Peter Karp from Admesi. Please, Peter.
Yeah, thank you. I would like to know, can you say something about the special challenges regarding color measurement?
Color measurement.
Or are there special challenges you encounter?
Well, I mean, frankly speaking, I do not fully get the direction of your question. But I mean, let's say if you compare OLED versus micro LED in micro displays, then as I mentioned earlier, the color purity of micro LED should be potentially be higher due to the narrower spectral characteristics. And so in terms of let's say color measurement, there should not be a big difference, but as I mentioned, color purity should be higher for micro LED micro displays if you're talking about full color micro displays, of course.
Okay, so then I would assume that the FHWM is more important in this case.
Yeah.
That you have a small FHWM. Okay, thank you.
That's true. That's true. Mm-hmm.
Thank you, Peter, for the question, and thank you again, for this interesting presentation. Thanks a lot. And now let's move over our third speaker, Jan-Matthijs Meulen, co-founder and CTO of Morphotonics. Will present a talk about large area nano imprinting for automotive applications. So please, Jan, the floor is yours.
Yes, thank you. In this presentation, we'd like to show the possibilities of nano imprinting to add optics for different automotive applications. And in our case, we use a special large area nano imprint technology, which we would like to explain. If you look at imprinting and optics, you see that there are a lot of opportunities there are for display where we can add, so you can add Fresnel lenses or anti-glare structures to increase the readability. But you can also think of diffractive waveguides used for AR and obviously also 3D or how do you say it, prisma lines to enhance the safety, so that you can treat the display aside. And all these topics, they can be solved by nano imprinting, by adding the textures onto the displays or inside of the displays. And these can be small displays, but for 3D, for instance, they can be really large display. Also for privacy application, can be large displays. And this is where within Morphotonics, we focus. So we are an equipment supplier. We sell equipment for the display market, where we can add nano or micron structures on large substrates for small or large applications. And hereby we can add any functionality, any optical functionality, ranging from very small optical elements, wide with polarizers, to really large one. And we do this from the Netherlands. So we have our clean room in Veldhoven, where we work with a small group of 40 people. We have our own technology, which we call large area nano imprinting, but we also call it roll-to-plate imprinting, which I will explain, where we do the process development, but also help our customers to scale, to enlarge the master or to develop the resins. And that is really important. So how does our technology looks like? We are not a standard roll-to-roll or a standard wafer scale method. We use multiple rollers, but we replicate onto a discrete substrate. We add the resin on the substrate and we press a flex stamp onto it. The flex stamp has an anti-stick layer, and therefore it's easily delaminated and can be reused again. And this is a scalable technology which we scaled up to Gen 5 size, 1.1 by 1.5 meter. And then every 2 minutes, an imprint can be made. The flex stamp can be reused many times, 500 times, 1,000 times, and that is eventually a cost advantage. But moreover, where could you use it? Where could you use it for the automotive applications? Well, you can think of various applications. Obviously, the 3D application, that's an area where you can see depth inside of your display, which might give less eye strain because you have a little bit more focus, like you see in front of you. So it's, apart from that, it's nice, nicely looking. It's also supposed to be slightly enhance the safety. You can also think of reducing the glare on your displays, that if the sunlight comes from the side, that you're not struck by light. You can think of HUDs. So here you see an example of diffractive waveguides, which we have replicated on Gen 5 size. And these are all, say, small, medium to even large size display, where it makes sense that you have the large area imprinting. But you can also use the large area nano imprinting to make a lot of small displays. Like here we have tiled 270 products. You can also add a lot of smaller sensors or projectors onto one imprint area. And this is what we do in practice. Well, we do both. Also here, what you see here is the Gen 5 size. Here you see on the right side, multiple products made in one imprint cycle. We do this accurately. We do this for different customers. We do this also within the Fabulous project. Fabulous is the European project for freeform micro-optics, and within this project we work together with Seisenberger on the lighting application, where we add optics on LEDs to direct the light. And this is quite a successful project. But you can also, with the topic of mini or micro LED applications, like the previous presentation, you can also think of smaller displays where you can add optics, micro lens arrays onto displays. And then you can steer the light projected. For instance, you can project on your side view, and thereby you can better show if there is a car next to you. Or you have the decorative application where if you open your door, there's a projection on the floor. And each of these applications can be, there's optics inside which can be replicated. Although for some of them, or most of them, you need alignment between the pixels and the micro lens arrays. And therefore, we have developed a new tool, a new imprint tool, still Gen 3 size, still 600 by 600 millimeter, where we have a position accuracy of plus or minus 3 micron, where we can position the lenses on the substrates according to alignment markers. This will not directly solve the issues of Vogel. If you have really small pixels of a few microns, then this 3 micron accuracy is still crude. But in the higher ranges, this might open opportunities. You can also think of dual-sided imprints, where you align the front imprint to the back, where you can reduce thicknesses layers and get more lightweighted optics. As shown here in this presentation, where you have you combine one optical element with the second optical element, resulting in the combined optics. We do this partly within the Fabulous project. I already mentioned it. This is really an interesting opportunity for all. So there is a chain from design to production, where all the parties they are inside and easy accessible to develop a new freeform micro optics applications. There's even the opportunity to get subsidized on the topics. There's currently an open call ongoing, so everybody can submit their proposals. yeah, and then one of the very nice results is this very nice decorative product, which maybe even for an automotive application can be interesting. And that brings me to the end of my talk. With large area nano imprinting, we can enhance the design, the functionality, and even the affordability of for automotive displays. We do this for small and large displays for different applications where we have aligned imprinting available in the end of this year. And the technology is already being used by many customers. Yeah, and we are happy to work together on this topic.
Thank you, Jan. Thank you very much for your presentation. Any question for Jan, please raise your hand. Yes, Kunal, please, from Porotech.
Yeah, I was just curious about, you were talking about some diffractive waveguide which you have done.
Yeah.
How about the efficiency of those type of waveguide which you do by the nano imprint?
Yeah, these were diffractive waveguides for augmented reality. We did it within a consortium. So we had the company Light Trends. They did the design. It's a simple green HoloLens design. We wanted to show feasibility, where the mastering was done by the NILT company, and we showed that it worked. It worked nicely. It worked as expected. So the design simulation showed exact same result with the actual AR waveguides inspected by a company, OptoFidelity, so by a third party. The resin was 1.9 refractive index. Also, the glass was supplied by Schott. But most importantly, the replication quality was stable over 100 imprints. And that is very important to show that the manufacturing really is possible. So the replication of diffractive waveguides is possible reproducibly. And that's what we showed.
And the efficiency in terms of that, we all know that waveguides are generally killing the brightness. So generally waveguides are, people are struggling double-digit efficiency. So is it any number which you have measured or something like that?
Yeah, we have looked at contrast measure levels, but I am not, OptoFidelity did, so the third party. Contract measurements were around, I thought, like the number of 8, but it's not sure how it compares to standard numbers, especially if it's also on the design not supposed to have the highest contrast. So that's therefore difficult to answer.
Okay, thank you, Dan.
Thank you, Kunal, for your question. Any other question for Jan? Please raise your hand. Okay, then thank you again. Okay, yeah, we have a question from Giovanni from Huawei, Giovanni Cotella. Please, Giovanni. Giovanni, we can't hear you now.
Hello, can you hear me?
Yeah, that's good.
I'm sorry. So just thank you for the presentation. I was wondering whether it's possible to make any, pretty random features with this method, and also if there is I know the race is to go smaller and smaller in features. I wonder if there is a limitation also on the larger side of the feature. So I don't know, tens of microns is an issue. So the question is about the shape, if it can be random, and which will be the maximum shape you can actually create.
Yeah, that's a good question. Well, random can be made for sure. Well, random in the micron or nano range, but there is not really a lower limit. So we've shown 50 nanometers, and smaller is possible. In that case, it's more on the aspect ratio rather than on the size. On the high end, there is a limit. I would say we go to few hundreds of microns, 100 micron, 200 micron, possibly depending for certain structures on the 500 micron, but that's really the upper limit. And this is also where, well, we work together within Fabulous with company SUS. They show really really good results as well, and they can go higher. They can go to the higher ranges.
Okay, thank you.
Thank you, Giovanni, for the question. And thank you again, Jan, for your interesting presentation. Thank you again. And it's a good transition to talk about Fabulous. So I will invite Jessica Van Eck, Managing Director of Fabulous, to talk about the European pilot line. So please, Jessica, so Jan, please just stop sharing your screen, and then Jessica will start.
Okay, yes, thank you so much, Jimmy. So I share my screen. So you see it now. Thank you for having this one slide indeed to introduce Fabulous. And thank you so much, Jan Matthijs. You also gave an excellent introduction already. So we are indeed a big group of partners, European RTOs and industrials that are together forming a pilot line for the design and manufacturing of freeform micro-optics. So you've heard of Fraunhofer FEP already, you've heard of Morphotonics already, and you will be hearing from CEA-Leti as well in this meeting. So it kind of also shows our strength in the automotive industry. But the idea of this group of companies is that together we can really offer a full value chain of support for freeform micro-optics. So we can support with modeling design, with origination, tooling, material, replication, quality control, and we even have integration partners. And so as part of the project, we've been already working with what we call the use cases. And I wanted to highlight a few applications here that I think are interesting for automotive. Of course, very relevant is the one we did with Hella on the automotive, on the headlights. So they have been working indeed to create this smaller optic for good light distribution in the headlights for the next generation headlight modules. And so here you see a really nice double-sided optic that we've created in Fabulous that is very promising for this application. Then Jan Matthijs already mentioned a little bit Seisenbacher, so the interior lighting, where you can also use micro-optics, freeform micro-optics, to get a really nice distribution and a lot of energy efficiency. So in the interior lighting, then also in the last slide of Jan Matthijs, that was indeed the Swarovski one, which is maybe not completely automotive, but of course it can be used in automotive to create maybe a really nice, interesting interior decorative lighting using such a structure. And finally, also, we've been working with micro OLEDs. They are doing displays in the sports glasses with AR that, of course, also very relevant to, the head-up displays that you see in automotive. So these are actual cases that we've already been working on that are relevant for automotive within Fabulous. Of course, we also know the light carpets from Swiss Micro-Optics. We have partners that are doing optics for LiDAR. So really quite a few things where micro-optics can play a role in automotive. And of course, if you have any questions, then you can go to our website, send an email to the info or ask Jeremy of EPIC for an introduction. And then, of course, the open call. So if you have any questions, the open call is running until end of the year for any company looking to integrate freeform micro-optics. So thank you, Jeremy, for allowing me to share this with this audience.
Yeah, thank you very much, Jessie. It's really relevant here, of course. So if you have any question, you can contact me as well, and I will be pleased to put you in touch with directly with Jessica. So thanks again, Jessica, for this introduction of Fabulous. And now let's start with William Lee, also product manager at AUO. We'll talk about micro LED displays are quickly becoming relevant in super luxury and sports vehicles. So please, William,
hello.
The floor is yours.
Hello, everyone. This is William. We are come from the AUO, And then I want to share some like new focus for the AUO automotive new approach, especially for the micro LED. I think we cook the new develop of the micro LED since 2019. Then we work on the 4 years program. Then we have a lot of people join together to show you some new progress. Okay. AUO, I think we are one of the main display maker, and now we will have more portion of the revenue come from the automotive display business. Then I think something will happen. We will take more resource to the automotive business and enlarge our business scope. And AUO, we have a 16 years experience in automotive product. Especially, we are the worldwide #1 CID application display solution provider. Then I think we have more knowledge. We can cook a new display technology to automotive based on our experience. When we do conventional LCD business, we are thinking what will be the next step. Now I think we have more and more products implement for the mini LED matrix backlight solution. And when we want to cook a next generation display, we are thinking how to reach more vivid display and with more amazing display solution. So we transfer to the micro LED. So we are defined when we go to the 2025. After this year, one of the contribution for the micro LED solution will also boost up AUO display business. And we try a different application, especially for the rollable display. I think we demo some concept for the 14-inch display, and also we cook some blendable display with a 2-layer approach. One will be the decoration film into our display, and we have very brightness display micro LED backplane to show the display behind of the decoration film. And the designer can do anything they want to do to hide the display. When we want to show the display, we call the demanding application, show the right timing for the contents, and everyone can just enjoy the elegant and also very premium luxury interior carpet design. And then for the next generation, we also cook some like technical material integration for the stretchable display. We can form the real 3D surface with our amazing micro LED solution. And then for this year, I think more and more people are talking about what will be the worldwide first micro LED mobile display solution. I think in this year, you will see one of the portable device, especially we call the wearable device, will use our micro LED as a first mass production micro LED display in the world. And the PPI will out of the 300 PPI. But for the micro LED in automotive, we are thinking we are defined 200 PPI is enough for our display in automotive. Then we also cook a 2 different approach. We call it, the first one will be the rigid type display with a standard form factor with a high brightness. And then we also adapt the new flexible substrate to produce a different form factor. And the designer can choose a different curvature and also stylish design with a very charming display solution. We are thinking some of the advantage of a micro LED display. The first one, we want to highlight a freeform. I think for the true circle is no longer an issue for this kind of the watches, but also when we want to produce one of the knob application in automotive. Some of the designer cannot just put the knob to like a flat tire shape. And for the micro LED solution, we can produce a true circle display. And for the durability, I think compared with OLED solution, we are thinking the inorganic substrate like micro LED we can produce a very long life durability, especially no luminous drop. When we do the test, even in the high temperature 85-degree operation, we can keep the luminous still 80% more over 50,000 hours driving. And then for the third part, I want to introduce the high transmittance, especially for the transparent display. It's one of the also top topics for all the designer and also the integrator want to show the display with a transparent behavior. But they will be the one of display on demand solution we can produce. And AO now we can produce a very good 60% transmittance at 100 ppi solution. And this year we show some real sample and the demo on the AUO collaborate, especially in Taiwan, Kaohsiung city. We show some public transportation information display with a transparent micro-LED solution. And then for the vivid color and also the visual inspection, I think for the wide viewing angle solution, there will be the upgrade to compare to the LCD and also the OLED solution. Even OLED have a very good color gamma, but for micro LED, we can also improve the vivid color solution. And then for the wide viewing angle, I will show some measurement data to you later. When you see the display from any viewing angle, you have the same performance, especially for the viewing luminous. It's quite amazing for the application. Everyone, you can see one of the uniform viewing angle properties, and every designer think that this is the amazing solution for the display. Especially for the sunlight reliability, our micro LED solution can easily drive to 2000 nits, even 3000 nits. And for some indirect view solution, we can also produce 50,000 nits without the polarizer. So when we want to against the sunlight exposure in some special case, I think micro LED will also produce a very good integration for that. This is a very important slide to show you when we compare with a conventional display like AMOLED, micro LED have a best property, especially for the viewing angle. You can see for the wide viewing angle point of view, you can see will be consistent luminous, even compared to the center, we call the perpendicular angle. We can have the same luminous. And if we put the measurement to the, we call the German OEM viewing angle, we can see very consistent brightness and compare with the OLED solution. If we calculate the real power efficiency, definitely it will be higher, maybe 50% of the AMOLED solution. So there will be one of the idea we want to share to our automotive partner. You can think different because you will not be limited by the traditional display. And there will be one of our idea when we do the micro LED display, we come from the rigid type rectangular one. Then we also adapt a new solution to have the coating decoration film on the top. And then for the freeform now, through circle, curvature, and the stretchable, we are also ready for the inquiry. So we are looking for the new generation display with a different form factor. And for the flexible, I think is the intrinsic property for the LED solution, because if we can do the substrate with the flexible type material, we can easily integrate to the flexible type display. And then the last part, I want to point out the transparent display with micro LED, because we have high transmittance and also very bright display quality. So everyone can use this as an outdoor display. So even for the automotive application, we can apply the display to our glass area. And for the blended, sometimes people say the shy-tech solution. I think we have a very good viewing angle performance. So we produce a very like a charming display with a decoration film. Then you can easily integrate your idea to every surface with a decoration part. So this is the latest slide I want to show you why the luxury brand, especially for the space super sports car, want to integrate this solution into their display component, because we have the opportunity can reach the very high brightness, over 50,000 nits, and the long lifetime. Automotive display want to reach a high temperature operation. If we compare to the traditional OLED, it will be under different scenario. And then for the best optics, especially the viewing angle and also the color shift, there is no constraint for the viewing angle. It's a perfect display type. If you want to reach the last topic, will be the transparent, over 60% transparent. I think at 100 ppi, we already can produce a very good solution to you. So this is today I share to you why the automotive customer want to adapt the new micro LED display for the next generation vehicle. Thank you very much.
Thank you very much, William. Just a question from my side. Are all these products are already available for the customer?
Yeah. So our plan is to introduce the display micro LED mass production in 2026. And for the last year is a very important year. 2022, we already got the the agreement with some premium OEM. They want to adapt the new developed project with a micro LED technology. So now we are solving the industrialization issues, especially high yield rate and the low repair process. We want to make it like more cost effective. Yeah, that will be the current progress. Okay. Yeah.
Okay, thank you very much. Really impressive. Yes, a question from Vygintas Jankus from the CEA-Leti, please.
Yes, thank you. Thank you very much for the interesting talk. You write, yeah, exactly on the slide, sensor integrated display. What do you mean? You mean sensor integrated in display? And yeah. If yes, what functions you target first?
Yeah, in AO we have the, like a fingerprint and also the ambient light sensor integrate into the AA area.
You said fingerprint and what was the second?
And the ambient light and also camera.
Okay, yeah. Clear. Thanks.
Yeah.
Thank you, Vygintas, for a question. Yes, Kevin Gagan from Corning, please.
Yes, William, thank you. I had a question about the backplane technologies that you're deploying in each of these different modes. Can you speak about that for the transparent and flexible and stretchable?
Okay, for the first one, we'll talk about the transparent one, right? Okay, the transparent, now we can reach like a 60% transmittance within the 100 ppi display. Now we can also reach the 1000 nits. Yeah, but there are two different approach. Some of the customer want to have higher transmittance, and some of the customer want to reach higher brightness. So we will develop two branch. The first one, we will reach a high brightness. Then we will think about how to overcome the transparency, because there are different stake. And regarding for the different like a transparent material, like a additional layer for the background with a black or some switchable display LCD, we also think about the feasibility. Yeah, there will be the next generation integration part. Yeah.
Thank you. Thank you, Kevin, for a question. Yes, Kunal, please, from Porotech.
My question is again for the transparent display. For the transparent display, generally the main cause of losing transparency is the metal lines on the TFT. So how AUO is approaching that particular problem? Can you tell us a little bit about that?
Yeah, I think we cannot just avoid the metal line. Yeah, we still need to have the metal line, but we can shrink the LED size. Even we can choose small LED chips, but we have a very important issue. We want to keep the same good power efficiency, especially for the quantum effect. I think there will be the drop a lot of the energy efficiency. So we are looking for the improvement for the LEDs from the LED supplier, how to shrink the size and also keep the same performance. Yeah.
Okay. So basically, if the LED size is going, then transparency problem will be, if small LED size can have the better efficiency, then the transparency problem can be solved.
Yeah, I think the target will be 70%, but we're still working on this topic, how to overcome the 70%. Yeah.
Okay, thank you. Thank you.
Thank you, Kunal, for the question. We please from Fraunhofer FEP.
Yes, thanks as well for this talk. Could you please go back a few slides where you showed the angle, the viewing angle dependency?
Yeah, this one.
I was wondering a little bit about that. I mean, I'm more coming, let's say, from the OLED side and have some yet limited experience with micro LED. But in general, OLED is a Lambertian emitter. Of course, I understand, let's say, that a lot of the displays on the market are OLED top emitters, and there's not really Lambertian anymore. But still, let's say, the emission cones of OLED are typically much wider than of LED or micro LED. So how do you explain that behavior?
Because I think for the AMOLED solution, still have some like angle be shaded by some spectral structure, especially the structure. I think the viewing property, especially the light distribution, also be constrained by the structure. But for the micro LED, we can see the top emission, and also there will be no constraint for this structure behavior to change the light propagation. So there will be one of the idea we explain why the micro LED solution can have better viewing angle performance. And I think for the AMOLED, not only for the brightness, we can see for the color shift is also a very critical issues. But for the micro LED, we have the data. We can also compete with the AMOLED solution. So basically, for the viewing angle performance, if we compare to the AMOLED, definitely we cannot see any weakness for the micro LED. But do you have any different opinion for the AMOLED solution? Because we are thinking there will be one of the intrinsic property for the AMOLED pixel structure. Yeah.
Okay, thank you very much.
Yeah.
Thank you, Louis. And yes, Giovanni Cutella from Huawei, please.
Hi, thank you for the presentation. Very interesting. Just I'm wondering for the product you mentioned that should be out this year for wearables application, which type of architecture are you going to use? If it will be RGB micro LEDs or like blue micro LEDs with color converters?
Mm-hmm. Now I think we will use the RGB LED for the consumer product. And our team, I think in next generation for automotive, we will use the color conversion. But we also find some new improvement for the red color LED. So for the first generation, we will choose color conversion stack for the automotive product. But for the next generation, second generation, we are thinking the feasibility for the RGB type. Yeah.
Okay. Well, for wearable will be RGB then.
Yeah, yeah. Now will be the BG and BG color LED and the color conversion R. Yeah.
Ah, okay. I see.
Yeah.
Okay. Thank you.
Thank you, Giovanni, for your interest, and thank you again, William, for your presentation. Thanks a lot. And it's also a good transition to talk about color, and we have now Kunal Kashyap, Vice President, Display and Head of Taiwan from Porotech, who will talk about DPT, the ultimate solution for microdisplays. So please, William, if you can stop sharing your screen. Thank you. And Kunal, you can share your screen and start, please. And don't forget to unmute yourself.
So can you hear and
yes.
see my presentation? Yes. So today I'm going to talk about our unique technology, which is called a dynamic pixel tuning. And that is for the micro displays, as well as either it can be used for automotive application or as well as the smaller size of the display, both of the applications. So basically, I will talk a little bit about our company, then their technology and what we are going to do, what is our plans. So let me introduce our company. We are a very young company. We just spin out from the Cambridge University in 2020. And most of us are having a lots of R&D experience for more than 15 years in GaN field. And we are having a good patent portfolio, which is nearly around more than 70 patents around this GaN technology. And we also produced our first in-GaN red, which was in November 2020. And then we aggressively tried to do the same micro displays on and produce all the 3 colors with the brightness of the nearly around 2 million nits, max brightness of the 2 million nits in the green color in November 2021. And then we came up with a new approach, which is a single pixel. We call it DPT, which single pixel can produce all types of color, and which we demonstrated in the SID conference display week in 2022, and we won the best prototype award there. And we also moved towards 200 millimeter, and now we are moving towards 300 millimeter, and we are expecting it to come with a 300 millimeter LED approach on 2023. And then finally, we are doing some kind of working with our display partners as well as the backplane partners to utilize the DPT technology completely on a product level. So basically, all the things are done on the PoroGaN. PoroGaN means we are doing some kind of porosification on the GaN structure. So we are tackling all the issues from the material perspective itself. So basically, we are playing with the stress manipulation. So these porous structures we can design, we can do the way we want, and that can manipulate the stress that we want. We want to reduce the stress, we can reduce the stress. We want to increase the stress, we can increase the stress. As well as it can affect the band gap as well as the inclination of the band gap, and that enables us to become to make a very stable color as well as tunable color, both. So the left side, you are seeing that we can have any type of color on in-GaN material from red up to blue, all visible, very stable color. Very stable color means we don't have the shift in 2 order of the current density. We try to keep it as stable as possible. As well as dynamic pixel tuning, where we want to shift from the same pixel, from the same surface to single emitter, we can emit all type of visible spectrum. That is what is called the dynamic pixel tuning. And the direct advantage of the dynamic pixel tuning is that where people have to work on sub-pixel concept, where they have to do red, green, blue, that type of LED sub-pixels, we can do a larger emitter size and with keeping the same resolution, or at the same time we can increase the pixel density, keeping the same chip size. So in that case, we can have the larger pixel density, we can have improved brightness, and as well as where people have to work on 3 different material systems, we can work on the single material system, which can enable us to consume less power, as well as it can extensively reduce the cost, because when people are talking about the mass transfer, this type of technology with the smaller pixel, where again the pixel size is limited, where we cannot go beyond 10 micrometer pixel size, we can do everything on the larger pixel size. We don't need to do the mass transfer. We can directly do a wafer to wafer bonding, because one LED wafer, one type of CMOS driver or any type of TFT, we can just directly bond it on a single substrate. So that enables and that solves lots of manufacturability problem, as well as enhance the performance, overall performance. And as well as just now William was talking about AU, that the transparent displays, they are suffering because they are looking for a very good high efficiency emitters with a small pixel size. This type of solution can be a promising in that type of application. So, and the second thing is that all of them are where people are talking about the mass transfer, working on 3 different material systems. They have to do 3 different steps of the mass transfer, and they have to do the pinning and this type of thing, which requires a lot of additional step and additional cost. And we don't need to do that. We just need a single emitter, single wafer of the LEDs, which can emit all type of colors, and we just do the wafer to wafer bonding. As well as this, all these things are on in-GaN material. And we know that L-in gap or gallium arsenide, that type of things are more prone when there's a size dependency is coming, and in-GaN material are less prone in terms of the size dependency. So our solutions are all on in-GaN, so that even for the smaller size, we have a higher efficiency of the emitters. And like we say, in terms of the manufacturability, first you have to deal with all the blue materials, do the mass transfer or pick and place, whatever we do, and then the chip bonding, and then whatever integration we have to do on the backplane from the driving part. So 3 design needed for R, G, and B. And for the green also, then we have to deal with a separate material system, which is L-in gap or gallium arsenide red material. And then we have to do the same mass transfer process, 3-time mass transfer process. If we assume that each time mass transfer process is 70% or 80%, then 3 times it is going to be less than, say, 20-25%, and that is resulting in the higher cost of the products, and that is very difficult to get into the market for the consumer products. So when we are talking about the small pixel size, less than 10 micrometer or even 20 micrometer, people are struggling with the yield loss, and this can reduce our yield loss by 3 times, because we only need to do the things on one single step, which is like this, where we will just choose one DPT material, one chip manufacturing, like a LED, single LED, and then single air singulation. Either we can do the pick and place, mass transfer, or wafer to wafer bonding, this type of things which improve the yields significantly. And then we choose the integration on the back plane, and then these whole things can do on a single material system, single design, which can effectively reduce the cost and the power consumption by 80%. And these all are applicable to all type of direct view, as well as the HUD type of the markets, or tablets, or wearables, as well as the micro displays for the AR/VR applications. So if we talk about the transparent display, we just use our micro LEDs, and we just use some off-self backplane and just a smaller emitter size, and then we try to do some kind of transparent displays on the available, means we didn't do any kind of backplane, we just take it off self backplanes, and which is nearly 40 ppi, not a very good in terms of the ppi. And then we demonstrated that what type of displays we can do in terms of our material system, where we put our red, green, blue and material together, and then you can see that we can achieve a quite good color combination, as well as the color gamut. And in terms of the DPT, we also did several prototypes where we demonstrated that how we are going to achieve all the colors from a single material system, from a single LED. So if you see in this, these all are based on the DPT concept, where we are showing that how we are going to do the color mixing, and it is on a single LED. So chip level, we can produce different type of colors, just from red to blue, as well as on the active matrix. Also, we show these active matrix backplane was on the LCOS backplane, just off-self backplane, means there is no special design we have done for that demonstration. And then you can see that each frame, from the frame wise, we can achieve from blue to red all type of colors from a single backplane. So overall, this DPT concept is going to reduce the complexity of the whole micro display. Either it is for the automotive application, or either it is for the AR/VR application, or either even it is for the wearable or TV signage, that type of application, because you have to deal only single material system. And you can even do the larger emitter size if you want a higher efficiency or higher luminance, because the emitter size is important in terms of the enhancing the luminance. As well as if you want a higher transparency, you can reduce the size because you don't need to deal with the 3 subpixel system. You can do or you can use 1 subpixel and then other 2 subpixels are just empty. So it can be a blank. So it is direct impact that how the transparency is going to improve. And the only transparency will be affected by the metal lines, not by the not by the micro LEDs. And if we are talking about the metal lines, you have to deal only 1 single LED metal lines. You don't need to do red, green, blue metal lines. So most of the part of the display can be completely empty. So that can directly impact the transparency which people are trying to solve. And I think if AUO have demonstrated something which is 60% transparency, if this type of technology where they can reduce the metal line by third, then it is very easily achievable by that transparency can go beyond 80-85%. So this is all about how the DPT is going to impact the micro display as well as the all type of display manufacturing as well as the performance wise. So this is what actually is my talk, to just demonstrate what actually DPT is, what is its functionality, and how it's going to affect the whole market.
Thanks a lot, Kunal, for this really interesting presentation. And we have already 2 questions. Benjamin, please, you can start from Forvia.
So I have 2 questions. So basically, what is your status right now in terms of prototype, mass production, and things like that? Second question, reliability. What kind of tests did you perform with this new kind of LED type?
Okay, so your first question, our status is that we are at the prototyping stage because we are working with our backplane partners who is trying to do some kind of backplane which can enable us to actually not doing it frame by frame, means actual active matrix. So once that type of backplane is available, we can easily demonstrate the full color solution. So that is what is the prototyping stage. And in terms of the reliability, we have done some kind of reliability so that how this is not going to change in terms of the color gamut curve. So we have done a very stressed test for more than 500 hours, and the curves remain same. So, and I think that is, and we are also doing the normal LED like 85, this type of reliability test, but that is more like a similar thing which will be happening for all the LEDs. This will be also the same impact because we are not doing any special design, or we are not doing any kind of stacking, or we are not doing any kind of horizontal stacking or the vertical stack. It is just a single LED, single set of the quantum well. So it is just a single LED. So what LED is having the problem or advantage, this LED will be having the same advantage. So in terms of the reliability, we already confirmed that the slope or the curve which need to obtain for the color gamut all will remain same for 500 hours, and other part are less of our concern because it is just a single LED.
Okay, thank you.
Thank you, Benjamin. And yes, please, Stefan Ludgen from Meta, please ask your question.
Yeah, thank you very much for the interesting talk here. My question is, in view of efficiency of red, where you may limited with the performance, and is it in-galp red or is it in-gun red? Maybe I guess these are still the limiting factors. And when we see your DPT panels, this is pretty dim. Yeah. So the question is, how can you overcome this problem in view of efficiency, or do you have any wall plug efficiency or any EQE data for red, which is the limiting here, I guess?
So, okay. So I will talk in 2 different perspectives. The first, we have in-GaN red, means which is stable in-GaN red, and we are approaching in-GaN red with a 30 micron pixel size. We have measured our efficiency is nearly around double digit, that is nearly around 10%. So 30 micron pixel in-GaN red is nearly around 10%, which we are targeting next year to improve by 15%. So that is for the single color. Now we come to the DPT one, and in terms of the DPT one, our if I explain in correct way, the DPT is less concerned of EQE numbers because for the EQE for the driving part, we need to put the current density to achieve the different colors. So in terms of that, if you think we need a low current density to achieve red and higher current density to achieve blue, as well as in terms of compensating the brightness, we are playing with the duty cycle, where blue need to have a smaller duty cycle, which is operating at the higher current density, which is a good thing for us because that can reduce the power. And in terms of the red color, where we are going to consume max of the duty cycle, which will be nearly around 95 to 97% of the duty cycle, which is operating at the low current density. So our approach to keep improving is that that particular slope of the current density where we are achieving from red to blue, we are trying to inject more current density in red and reduce the current density in terms of in blue. So that will compensate the brightness. So that will be our approach and the solution.
Or maybe in other metrics here. So you mentioned the performance of the I don't know if it was EQE or wall plug efficiency from 10% to 20%. What is the
EQE number?
That was the EQE number, okay. And but that was for a pretty large microLED, which is fine for the automotive application. Yeah, is the DPT, the power consumption, something where you said this is a big advantage? What would be roughly the power consumption or the wall plug efficiency of the DPT display then?
If we talk about the power consumption and considering the duty cycle, we have calculated for the micro displays for pixel size of 3.5 micron and the display active area is nearly around 0.26. In our calculation, it is nearly around at the moment it is nearly around going to be 0.5 watt.
0.5 watt. Okay. 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 Thank you.
Thank you.
That is because of the limitation of available backplane. Once we have the backplane, proper backplane, then this is significantly going to be reduced.
Okay. Okay.
Thank you, Stefan, for a question. Yes, we have two more questions. Please, Christian, if you can make it short, and please also, Kunal, a short answer.
You mean me? Okay, Christian van der Sluijs here from Cryptic. I was trying to find out when Porotech is ready for a prototype with clients, and in what format.
Yeah, we are for the full prototype. We are working with our backplane partners, and we hope it to be next year, in some way around next year, early next year or the mid of the next year. We will be coming up with this solution on the full color panel.
Thank you.
Thank you, Christian. And yes, last question from Giovanni Cotella. Huawei, please.
Hi, thank you for the presentation. Just a quick one on the color purity of this dynamic DPT. And also, like in the demo I saw at SID and this year on the top left, I see that there is no blue in that demo. I was wondering whether there is an issue there, or like, I mean, why you decided not to have the blue pixel in the demo. And yeah.
Okay, the thing was that if you see the left side of the demo, that was on PCB, and the PCB, the ICs which we choose to drive it was not having that large range of current density. So that's why we were not able to achieve to the blue. But at the same time, if you see the demonstration in chip level, we are achieving all the colors, which is the right side of the top right side.
Okay. And the color purity of this mode is sufficient? I mean, which color gamut you can achieve?
Currently, in terms of the volume, color volume, we are able to achieve DCI.
Okay. Okay, I see. Thank you.
Thank you, Giovanni. And thank you again, Kunal, for this really interesting presentation. It raised a lot of interest. Thanks a lot.
Thank you.
And let's continue, yes, with Benjamin Willeke, Innovation Management and Scouting at Forvia. We'll talk about exterior displays for automotive. So please, Benjamin, you can start your presentation.
Okay, so thank you very much. I'm working with HELLA since 10 years, and since 1.5 years, we, let's say, more or less intensified our development in exterior displays, and I would like to give you a short overview and some insights what we are doing there. So I will start with exterior display requirements. Then I will go on with some content definitions, and then I will do a short deep dive onto the technology that we are focusing and see promising for exterior displays for automotive. So let me start with the requirements. So from the requirement side, we see that when you have a comparison between automotive and consumer, we see that especially temperature, warranty, brightness, shape, and curvature are additional or harder requirements compared to consumer displays. In terms of resolution, automotive is less critical, but maybe let's deep dive into what is a good resolution for automotive exterior. This is also a very interesting topic from our side. So what we did is we have a huge light tunnel, so we set up 4 different displays with 4 different LED display technologies, and showed some use cases to some participants and also some letters. And we found out that, for example, for a 50-meter distance, the readability is best for 13 centimeters text height. If you reduce this is a typical distance in a driving situation outside of a city. If the distance is at least 20 meters, this is a typical distance for driving inside of a city, 10 ppi, so 2.5 millimeter pitch is sufficient, and also larger is okay. More details that we found are that it's very important to have gapless images or hide the gaps within the use case, do not have any hotspots that are disturbing, and it's very important to have an easy understanding of the displayed information. So, for example, with this arrows here, it wasn't even easy readable for every participant what we would like to say with this. So it's very important that the content is known by all road users. So let's concentrate on, the content. From a content perspective, we differentiate between segmented and pixelated content. So segmented means you can define 1 or 2 or 3, a couple of contents that is predefined, and then enlight the area that shows the content, but it's not 100% customizable. And in terms of communication, with a pixelated approach, you're free to apply every communication or customization scenario you would like to. So let's quickly go into a short deep dive into the technology. From technology point of view, we derive into 3 kind of displays: the emissive display, the transmissive display, and the reflective display. Today, I would like to focus on the emissive display for this talk. So for the emissive displays, we see LED matrix, a communication matrix, smart glass, and the OLED. Today, I will focus on LED matrix and the smart glass. The communication matrix is a very high pixel pitch, so not interesting for us today. And OLED, there we see for exterior displays or exterior applications, there are OLEDs on the street right now, but the demand from customers for new OLEDs for exterior is very limited, let's say it this way. So I will focus first on smart glass and then give some insights on the LED matrix, how we see this. So when we compare both, the LED matrix has a very good contrast. If we are not using diffusers, it's possible to create a high brightness and multicolor, of course. And the main benefit for the smart glass is, if you see the image, it's black with white housings of the LEDs. And if you switch the smart glass off, you can generate this love black panel effect that all our customers would like to have. And it is possible to have a, let's say, passive display. So you switch the light off and you can use a reflective mode to also modify the reflected sunlight and show some, let's say graphics also when no light is on here. So I will start with a smart glass first. The smart glass itself consists of a dye-doped liquid crystal, 2 conductive films, and a substrate. If the liquid crystal is switched on, then a light can transfer through the cell. And if the cell is switched off, there's roughly, depending on the use case and the configuration, 5% light remaining. So contrast, let's say it's medium, but it's possible to show some graphics, to show some symbols and also text. For the short term, 2-dimensional is possible, but we're working also on 3-dimensional, so a curved version. We had a demonstrator this year on the CES, and the main benefits are you can communicate with low energy display in a medium resolution. How this could look like, I would like to show you in a very short video. So basically, this is the setup that was presented on the CES this year. It consists of flat lights, creating the backlight. And in addition, the smart glass in front, so that the backlight can be modified and communication is possible, as you saw with this kind of examples. So next technology I would like to deep dive is the LED display. Here I just want to give a short overview what kind of differentiation we are doing. So we have displays available for the classic automotive LED with a typical pitch of 4 to 5 millimeter, luminance values around 5,000 nits. Advantages are robust, mature, and contrast. So it's important to have automotive qualified LED for exterior use available. That's possible here. So basic setup can be an LED array on a PCBA, an optional diffuser, and of course a cover lens for protecting that we already have in every headlamp or rear lamp. On the bottom left, you see one of the examples we realized with a 4 millimeter pitch, and on the small images here, you can see that also with a 4 millimeter pitch, some very nice images are possible in red color. So when we go a bit lower with the resolution, we see the mini automotive LED. Here we have already automotive qualified LEDs available. The basic setup is that we have more LEDs with a smaller pitch on the same size compared to the classical LED. There's an optional diffuser possible, and of course the cover lens. The typical pitch is less than 3 millimeters. That's what we also found out is enough, or there's a lower limit what is helpful in communication that we found out in our light tunnel study. Luminance is also here possible above 5,000 nits, no problem at all. And yeah, same benefits. It's robust, mature, and the contrast is quite good. And one high disadvantage right now is that the mini LED and the amount of pixels have a high cost, but we are working on that together with LED suppliers to find a solution. And here on the top bottom left side, there's the first prototype that we made with such a mini automotive LED. So if we go lower with the pixel pitch, we talk about things like less than 0.5 millimeter, so even smaller than the CSP LEDs. We see luminances in the range of 2000 nits, have the advantage of a high resolution, but right now see no exterior automotive qualified solutions. So it might be that there are solutions available for interior, but for exterior with a very harsh environment, we don't know that there is one concept available today. So let me sum up what I just presented. So basically, micro LEDs do not fulfill exterior automotive requirements yet. Forvia is working on exterior displays since 1.5 years in a deep dive, and we are always interested in new technologies. So if you see things that can be realized, feel free to contact me for this. Thank you very much for your attention, and yeah, feel free to ask some questions.
Thank you, Benjamin, for your presentation. Any question for Benjamin, please? Yes, Louis.
Yes, thanks for the nice talk. So here on this last slide, you again mentioned micro LED do not fulfill exterior automotive requirements yet. Mm-hmm. You already referred to the more harsh environment for exterior versus interior light and so on. But what are the, let's say, the typical parameters? Is it about temperature? Is it about humidity? About whatever? What is it?
Oh, mostly, yeah, I can answer that. So mostly it's about a combination of temperature, -40 till +120 degrees Celsius. In addition, the LED should be switched on, not over the complete range, but in a, let's say, range until +50, +70 degrees. That depends on the customer wishes. And this combined with sunlight. So we have a very, let's say, bad combination, heating by sun, radiation, the engine or the battery pack that will heat up the environment, and the LED itself is switched on and generates heat in addition. So that are, let's say, the 3 or 4 environmental criteria that this technology needs to fulfill.
Okay, thank you. And another question, if I still may add, you also compared OLED, let's say, one of your initial slides, you can see OLED exterior lights, and that there's no, let's say, big demand on this, or maybe there was not really a big demand in the past, but there's no demand anymore, at least. So do you think this will change again with micro LED? And if so, why?
So I can just answer this question for exterior lighting applications. And I think if the costs are down to a feasible amount, it will be interesting for OEMs.
Okay, thank you.
Thank you for the question. And yes, Jensik, please, a short question. Jensik Kim from Axetris.
Thank you. Thanks, Benjamin, for presentation. About the flat light, in the description in your website, it's mentioned it's based on the micro-optics technology. What kind of micro-optics is involved?
Let me say it this way, without revealing too much. We have micro optics that will help to have to improve the uniformity. So we have a light guide, and the micro optics are used to extract the light perpendicular to the light guide.
Okay, and that's in your smart glass, or it's additional like a plastic molded product? Smart glass.
It's
okay.
part of the smart glass.
Okay,
yes.
Thank you very much.
Thank you, Matthijs.
It's part of the flat light. Sorry, smart glasses.
Yeah,
the backlight. Thank you.
And yeah, thank you very much, Benjamin, for your presentation. Thanks a lot. Really
Thank
interesting.
you.
And now our last but not least speaker of the day. So Vygintas Jankus, Business Development Manager at CEA-Leti. We'll talk about micro technology at CEA-Leti. So please, Vig, you can start your presentation.
Yeah, okay. So I'll have to be very quick. Okay, so first CEA-Leti at a glance. Just a quick introduction for those people who are not familiar with our institute. So, okay, first it's based in Grenoble near French Alps, and it's around 2,000 people who work at CEA-Leti. We have a large part at portfolio, and large part of those patents are under license agreement. That already indicates that large part of our revenues come from IP, license IP. And then another very important message from the slide is that large part, 85% of our budget comes from R&D contracts. So in other words, a lot of our revenues come from the development on demand, so to say, or from partnerships. So basically, we try to help companies to improve their products. So here is just a couple of examples of our innovations that are in the products. I don't go into details here. Is again just to emphasize that the way we work at CEA-Leti is by working together with the companies and working together with the companies on their product roadmaps and helping to improve their products and advance and tackle challenges within the technical problems that companies meet on the road. So for example, we worked for many years with ST Microelectronics on CMOS image sensors. Soitec is one of the most famous startups from CEA-Leti, actually, that became a multi-billion company. And if we speak about displays, so the company that works on micro OLED displays is called also Micro OLED. That is doing really well recently. And of course, Aledia is our startup that is trying to commercialize micro LED technology. And so our key asset is the clean room, the 11 square meter clean room space with 700 state-of-the-art tools, lithography, etching, and bonding tools, and so on. And we have many technological baselines. And okay, so one of those baselines that is relevant for today is this micro LED display, a technological baseline. But the key message from the slide is that we have a lot of synergies within CEA-Leti, and for example, a lot of know-how, process know-how, pixelization development, bonding know-how comes from other fields also, like, I don't know, power electronics or 3.5 semiconductors process baselines. So we can inject experts from other fields in order to have synergies and help solve problems within the display field. So display activities within the Department of Optics and Photonics, where we mostly work with kind of display applications, or applications also that could target automotive lighting. So we still work on LCD technology. We have a couple of collaborations, long-term collaborations here. We of course work on OLED, and major activities are on gallium nitride micro LED displays. So in principle, we have many competencies and skills from simulations and design. We also do epitaxy development. And of course, wafer process, that is our key asset. And integration technology is ASIC, or backplane and gallium nitride wafer integrating technologies that I will discuss a bit more later is also our key strength. So if you're speaking about micro LED and CMOS, CEA-Leti proposes various options to do this integration, and we have experience in those options, not only micro LED application field, but also in other applications like sensors and so on. So there's a lot of know-how on this. So we do standard hybridization, die to wafer with alignment, microtubes, so-called bumps, but we also do so-called monolithic integration, what we call direct bonding, where we first of all bond gallium nitride wafer on CMOS active matrix, and only then do the pixelization, which means that resolution in principle is limited by lithography, and of course other physical limitations of gallium nitride excitons. But another option, another way we do bonding is via standard hybrid bonding, where we first of all deposit I don't know, copper or oxide interlayers and then bond to active matrix, in this case with alignment, but in this case die to wafer is also possible, not only wafer to wafer like here. So a couple of demonstrators just to give a taster. So most of them, as mentioned, most of the collaborations we do are confidential. We cannot show too much results here, and these are the demonstrators, our demonstrators that we did, you know, with in collaborations that we can show, kind of more or less in public collaborations, public projects. So microtubes, we demonstrated, for example, bonding of display with microtubes, and we can do up to 10 microns with this technology. But here probably we couldn't go to lower pitches. So with direct metal bonding, we showed proof of concepts. There is a paper for those who are interested. I can send you later. Many years ago, we did a proof of concept of 2 micrometer size pitch. And finally, for hybrid bonding, here we have a couple of examples, a couple of proof of concepts where we show that we can bond gallium nitride wafer onto CMOS wafer of 3 and 5 micron pitch. And the final slide, so very short talk. So other results that we could share with you here is mainly from European project called Willeke in collaboration with Thales. Avionics here was it, and not everything, but most of those photos on the slide. And here just a couple of messages from the slide. So first, number one, on monochrome display, we really can do this. 1 million candela per meter square, 1 million nits is possible. And in this case, it was done with 10 micron pitch display, but we could go down towards 1 micron. We definitely know that it's possible. And finally, we work also on color conversion using quantum dots. So basically here we speak about blue micro LED and down conversion to red and green wavelengths. And finally, we also work, although maybe not to such an extent as Porotech, but also we work strongly and intensively on indium gallium nitride red or native color. So in this case here, I have a couple of examples that we published that I can share, and in this case is partially relaxed indium gallium nitride pseudo substrate that we got from Soitec, so-called Inganos, where you know the subsequent growth of gallium nitride and indium helps incorporate higher indium rate. Yeah. So just here a quick taster. We also do a bit more other work that at current stage we cannot share on this, and we would be, for example, very interested to exchange with Porotech at some point on this. And I think that will be all. Very quick presentation. I tried to make it fast. And any comments and questions?
Thank you, Vygintas, for your impressive capabilities. And do we have any question, please, for Vygintas? We're running a little bit late, but we have still a few minutes for question. Please feel free to raise your hand. Maybe I have a question for you, a short one, Vygintas. What are you expecting by the photonic community? Are you looking for potential partners? Are you looking for the customers, or maybe be a part of European project? What are you looking for here?
Actually, yeah. So we indeed we are looking for more partners within Europe. Indeed, so it can be either partners for European projects, so it can be just partners direct. We could contribute to our partners' product development, but in principle, indeed, yes, either collaborative, how to say, face-to-face collaboration, direct collaboration, or via European project. Correct, because we have mainly partnerships. So we have partners in France, kind of French-based partnerships, and all other our partners are actually outside Europe, to be honest. So it would be very interesting to improve our European presence.
Okay, great. Thanks a lot, Vygintas. So if you want to keep in touch with Vygintas from CEA-Leti, you can come to me. I will put you in contact with him. And it's the same for all the speakers today. If you want to be put in contact with our speakers, it's possible also for participants. And I would like to thank again all the speakers. It was really interesting. It was a lot of interest, a lot of questions, interesting discussion as well. So I would like to thank all the participants, all the speakers, and please feel free to contact me if you want to be put in contact with any of the participants of today's OTN. And I invite you, of course, to check our website for the next event you could take part, of course. So thanks a lot, and see you next time. Goodbye. Thank you.
Thank you.
Bye-bye.
Bye.
Thank you.
Thank you, everyone.
Bye.
Bye-bye. Thank you.
Goodbye, Christian.